for algae-based biofuels. I've been working under the advisement of Dr. Chris Bachman for the past 3 semesters. I'd like to begin with a short overview. I'll begin by motivating my study, why we want to develop petroleum alternatives. Why out of those petroleum alternatives do we want to pursue biodiesel? And then I'd like to talk about the main limiting factor for any renewable resource, which is energy return on investment. That's how much we're getting back out. Does it justify what we're putting into the system? Later on, I'll talk a little bit more about my project in particular. I'd like to begin by outlining our petroleum dependence. I focus on petroleum as opposed to other fossil fuels such as natural gas and coal, mainly because no sector is as heavily invested in a single resource as the transportation sector is with petroleum. The figure I have shows the primary energy consumption by source and sector for 2011. As you can guess, coal, a majority of that goes towards electric power, similar with nuclear power. But for petroleum, you can see that, you may not be able to read this figure, but I have it for you. 93% of the energy consumed in the transportation sector came from petroleum. Now that wouldn't be a problem if petroleum was a renewable resource, but it's not. Currently, proven reserves are about 1.5 trillion barrels. This number does rise and fall occasionally with new advents in technology for both discovery and recovery of petroleum, but that doesn't change the fact that we will run out eventually. Similarly, for the U.S., our reserves are about 23 billion barrels with a consumption rate of 6.87 billion barrels a year. I'll explain why that's going to be a problem. Economic and political motivations for developing petroleum alternatives. Currently, we import about 60% of our petroleum that we consume. Again, that's a problem because were that to not be the case, we wouldn't be able to last very long on our petroleum reserves. There's no security in being dependent on a foreign entity for the majority of our petroleum, especially when, as I'll explain, our economy is so driven by petroleum currently. On the left here, I have in dollars per barrel on a scale of from 1980 to 2013, the average price of oil for a couple large producers. On the right here, I have the cost of U.S. number 2 yellow corn, dollars per metric ton on the same time scale. As you can see, there's not a direct correlation, but it's hard not to notice the trends and how the price of oil affects the price of corn. Now, this is mainly due to transportation issues. When the cost of shipping increases for any product, that cost is reflected in the price for the consumer. The producers never absorb that cost. And so this could be any other crop, this could be electronics, but that will still be driven by the price of petroleum. Environmental motivations for developing petroleum alternatives. I think at this point we're past arguing the fact that greenhouse gases, including carbon dioxide, lead to global climate change. Atmospheric carbon dioxide levels recently surpassed 400 parts per million, with a large part of that being caused by the combustion of petroleum. 87% of human-based CO2 emissions come from the combustion of that fossil fuel. I was surprised a bit by this figure, which is the carbon dioxide emissions by major fuel. I would have thought that coal, with the coal-fired power plants, would be responsible for a large majority of our emissions, but it really does come from the petroleum combustion. A lot of that is planes, trucks, freight, and even just our main transportation, which is cars. So what are some alternatives to petroleum? Now these, again, because I'm talking about the transportation sector, I'm talking about are these suitable alternatives for transportation? So electric batteries, with the electricity being renewably generated by solar, wind, geothermal, etc. We really are okay with that for cars, but the weight to power ratio is not going to keep a plane aloft. Trucks are not going to be able to plug themselves in overnight. They just don't have the time for that. This requires an entirely new infrastructure to really work. Hydrogen is the same. We have those infrastructure problems. The storage and distribution of it is just not, it's a logistical nightmare at the moment, and until we get over that hurdle, it's really not feasible. Ethanol, butanol, and methanol, these are all alcohols produced by the fermentation of biomass. They use arable land. We need to grow these crops. And again, it does not fit into the existing infrastructure. We may see 10% blended ethanol, but we can't get past that and still run it in our vehicles. And even biodiesel itself has some drawbacks. Again, arable land to grow the biomass, and right now it's just not cost feasible as a petroleum replacement. But why out of those do we want to pursue biodiesel? We love solar panels. They take the sun's energy, the main source of energy on Earth, they convert it to, or they use it to create an electric potential which can then be used immediately or stored in batteries. These chloroplasts are these solar panels. They're taking the sun's energy and they're using that to create these chemical bonds for sugars, proteins, lipids. And at the same time, they're replicating themselves, they're self-assembling, they're healing themselves if they get damaged. The photosynthetic process sequesters CO2, which, as I mentioned earlier, is a growing problem. Not only that, but the lipids produced by these biomass are batteries, and I say that in the sense that there's energy stored within these chemical bonds that can be released later through combustion, in the same sense that batteries can store energy for being released later. Not only that, but lipids produce fungible fuels. We can refine these lipids in the same refineries that we refine crude. We can produce gasoline, biodiesel through other means, but we can also produce JP8, jet fuel, kerosene, and other fuels such as that, which can be pumped through our normal distribution systems. It can be pumped through pipelines for wide-scale distribution. I want to give an overview of our domestic biodiesel production currently. This shows the U.S. monthly biodiesel production for the past 3 years, with the greatest amount being produced in 2013, most recently, at 1.34 billion gallons. We do have the production capabilities of a little over 2 billion gallons, but currently we're just scaling up, we're ramping up production. In 1 month, December 13, the highest producing month that in 2013, it was 1.03 billion pounds of feedstock to produce that biodiesel. This is all feedstock that could be used for other types of food or just land that could be used for other crops. Soybeans remain the largest biodiesel feedstock at a little over 500 million pounds. That won't change even if we do adopt other feedstocks. Soybeans, due to their high fat content, they're used a lot in animal feed. And that fat content is just a little bit too high for those animals. So regardless of whether we're using other feedstocks, we're still going to be using a lot of soybeans. Why would we want to use algae as a feedstock in that case? They're highly productive, scalable, sustainable, and diverse in both their genetic potential and their co-products. I say they're highly productive. The lowest or the fastest doubling rate that we have for a wild-type algae is currently around 12 hours. This is to double. They're also high yielding. The table that I have demonstrates oil yield in gallons per acre for different crops. You can see the lower end of algae production is almost double that of the next highest oil-producing biomass. I wouldn't focus too much on that lower number, and I'll explain that in just a second. They're also scalable. We are already growing these algae on very large scales. If you hear about the ocean dead zones, these hypoxic zones, due to these massive algae blooms, we're actually growing those due to pumping nutrient-rich wastewater out from coastal cities. So we're already growing this ourselves. We just need to do it with a purpose and with a way to actually harvest it. They're sustainable. We're not using these arable lands to produce this algae. Even if we were growing in ponds on shore, we can do that in those desert areas in the southwest especially. Again, it sequesters CO2, and the co-products that come with it, animal feeds, these biopolymers, complex proteins that are able to be produced within a eukaryotic organism, are really going to drive the economics of this whole thing. When I say that they're diverse, there's no industrialized agriculture that focuses on a wild-type species. The corn that we grow had hundreds of years of selective breeding. It's had decades of genetic modification just to get to the yields that we're at right now. We don't have that time for these algae, but we can genetically modify them. And luckily enough, they've been working hard with natural selection to get us doubling rates of around 12 hours. There are algae that produce this 50% triglycerides by dry weight. And so by picking and choosing these genes for these aspects that we want, we will be able to get to an algae strain that may be able to produce that 10,000 gallons per acre. Okay, and so I'd like to talk about the number one limiting factor for any renewable energy, which is energy return on investment. If we're not getting enough out, if we're not getting enough energy out to justify what we're putting into it, you just don't use that fuel source. This will eventually happen with petroleum. Eventually it will not be enough. We will not be getting enough energy out to justify what we're putting in. Currently, petroleum is easy. It's already sitting in the ground. All we have to do is get it out and purify it. This refining into these different fuels. Algae, on the other hand, we need to have about 4 energy-intensive phases. This is the culturing of the algae, the harvesting of it, which usually traditionally is dewatering the algae, and then extracting these lipids from the algae, and again, refining them. JMU is developing a novel harvesting technique to skip the dewatering phase and move algal lipids to a higher energy return on investment and bring them a little more cost competitive with petroleum. So that ends really my motivation for the study. Why do we want to pursue algae-based biodiesel? And so I'll begin by talking about the JMU Alternative Fuel Vehicle Lab, where we did a lot of our research. My development of a continuous hexane recovery system, the data analysis of the testing, and the future directions for algae-based biofuels. So this harvesting process that I've been talking about, what it's really doing is taking algae in water, mixing it with hexane, and the output is these lipids that are suspended within the hexane. We have another output of the algae waste and salt water. We want to maximize that energy return on investment by really minimizing that waste stream. Right now, the hexane that we're using in this process is both expensive and environmentally hazardous. When we're spending $70 a gallon on this stuff, we can't just be throwing it away every single time. Otherwise, the cost is just enormous for a small amount of oil. Not only that, even if we did want to throw it away, we're not allowed to. It's regulated by the EPA as a hazardous air pollutant under the Clean Air Act. So Dr. Bachman and I decided that we need to develop a continuous flow hexane recovery system. Like I said before, the output of this other system is hexane, a solvent used to extract these lipids. It's very nonpolar, has a high affinity for nonpolar oils, and we need to recover the hexane from that, reuse it through the system, and also be left with the oil. So I determined the necessary heat duty necessary to evaporate a continuous stream of hexane, and I subsequently sized a heat exchanger capable of allowing that amount of heat transfer. From that data, I developed a 3D computer model based on that resulting data, and constructed a working prototype in collaboration with JMU safety officials. I'd like to thank Marcella Molinax for helping out with that. She really, she could have cut the project off at any time. Instead, she gave great advice on how we can continue with the project. She helped develop standard operating procedures for the safe operation and handling of my system for both me and current student researchers. So I'd like to thank her. So I need to develop a heat transfer model. Engineering Equation Solver is a software that I was introduced to in the ISAT program, in both my thermodynamics class and Dr. Chen's 413 Options in Energy Efficiency class. I use this program while working within existing parameters. There are certain things that I just wasn't able to change. I can't change the specific heat or boiling point of these fluids. I can't change the flow rate of the harvesting system. I need to work within these parameters. Again, temperature limitations, because our heating fluid is water, and we didn't have the capabilities of distributing steam as a heating fluid. We need to keep that temperature under 100 degrees C and still be able to provide that heat transfer. The point of the heat exchanger is that these two different fluids have two completely different boiling points. 68 C for the isomer of hexane that we were working with, and the oil that we were working with, it won't boil. It will actually smoke before it gets to that point, before combusting. We can't get anywhere near 250, 257 when working with water that's actually under 100 degrees Celsius. After developing that heat transfer model, I developed a three-dimensional computer model based on that data. It's a shell and tube heat exchanger, which is essentially a bundle of tubes used to increase the amount of heat transfer area within this heat exchanger. And I used an adaptation of a falling film evaporator, and I'll explain that here right now. So hexane micella flows in, hits a distributor ring, and it falls down to these 25 tubes. The grand total was around 0.2 square meter for this heat exchange area, which is the inside surface area of all these tubes. The idea is that on the inner diameter, these fluids will form a thin fluid, and as they fall down, sorry, I'll just play that all the way through. As the micella falls down through the heat exchanger, it's absorbing heat, and because it's such a small volume of liquid on the inside of these tubes, it just rapidly heats, and the vapors begin rising. And because that oil is not evaporating, it falls down to the bottom where it can be collected. While, as you can see here, those vapors will rise through and be condensed back down in this condenser. I also this early model was created in the free program Google SketchUp. It's a pretty basic CAD software. When I took this to the 3D printing lab to print out my model, I was informed that there are a little more technically advanced software such as SolidWorks that I could work with. I went ahead and I learned those softwares and subsequently printed a scaled down three-dimensional model of this, which you can actually see this tube bundle. I'll pass that around now, a little show and tell for y'all. Following this model, I began the fabrication of a working prototype. There are certain parts of this heat exchanger that I just didn't have the capabilities or the time of producing. So in SolidWorks, I produced some drawings for the JMU machine shop of parts that I needed to actually produce this model. I'd like to thank Mark Starnes for helping out with machining these pieces, and I'll actually pass around the two pieces. They're pretty basic, but I really just didn't have the capabilities or the time to produce them myself. I learned to weld for this project. This is the tube bundle here that I put together. Right now it's inside this shell, but this is what it looked like. I have baffles there to increase the turbulence of the heating fluid and to increase the amount of time that it is that it's in contact with these tubes. I really like the way that it ended up. And I also created a copper condensing coil for this condenser. You can see cooling fluid will go through that, and in the same way that water condenses on the outside of a cold water bottle, the hexane vapors will condense on the outside of this cooling coil. So here I am next to my model, and if you guys would like to come up and see it afterwards, I'd be more than happy to explain it to you. So testing the yes?
5 minutes.
5 minutes, okay. So testing and analysis. We ran 5 trials of 200 milliliters of this hexane oil micella at 20% oil concentration. That's 160 milliliters of hexane, 40 milliliters of oil. And we tested this to see 2 things. I proposed defining the efficiency of the system by 2 ways. Recovery efficiency. The whole idea was to get this hexane back and condense it. So are we getting enough out to justify, again, what we're putting into it? And to bring it all back to the energy return on energy invested, are we putting more energy into this project than we're actually getting out in that oil, in the energy density of that oil? So here are the results of the five tests. I'll be honest, I was happy to get anything back. To see this thing work was really gratifying. We're recovering about 69% of the hexane currently, 94% of the oil, which when you think about the amount of surface area within this heat exchanger, to only lose a few milliliters of this oil through each run, it's really impressive that we're actually getting it all back. The heat definitely decreases the viscosity and allows it to fall back down. There are vapor losses within the system that I believe could just be helped out by the introduction of check valves. And there was actually some residual hexane in the oil initially, and we had to run it through for multiple passes to retrieve that. This is really a hard way to determine the efficiency of the system. Because we were evaporating 100% of the hexane before this, getting anything back is an infinite increase in recovery rate. So I propose that the analysis of the energy return on investment is really a better way to go about it. The energy density of algal lipids, as figured out by Caleb Talbot through his previous student research, is about the same energy density as diesel. We did eventually get to run some algae oil, which I was very happy about. First time done at JMU to produce this algae oil and then recover it through hexane recovery and pass around just a little bit. But because we did the testing with soybean oil, we used the energy density of that soybean oil and the recovery rate to determine an energy rate output of the system, which this recovery rate, again, due to the way that we're feeding the system, could probably be doubled. So I would even put this number closer to 20 kilowatt. The energy input into the system, only about 3 energy inputs. The heating element used was 1.5 kilowatt. A 62 watt heating pump, or heating fluid pump, a thermally protected heating or fluid pump was used, and a 6 watt water pump. It's a submersible aquarium pump that we were used to pump the cold water through the system. The total energy input for that was 1.568 kilowatt, giving us a total energy return on investment for just this process, 6.4 to 1. So it is a positive energy return. But again, this is one part of a larger process. And there is no, we can get this as efficient as possible, but we still need to work towards greater energy efficiency in the culturing, that harvesting process, and even the refining process. And so there is really no one silver bullet for this problem. We'll talk a little bit about the outlook for algae-based biofuels. I don't believe that the biofuels themselves are going to be the driving force behind the development of technology. I think that the more cost-effective derivatives that I was talking about, these supplements that are selling for $5,000 a kilogram, that is what people are going to be developing this technology for. I believe that these biofuels will either be a co-product or they'll just piggyback on that technology development. The integration of algae cultivation into wastewater and high CO2 producing facilities. As I said, we're already growing this algae using that wastewater. We just need to do it on a scale that works for us. These high CO2 producing facilities, such as coal-fired power plants, by using algae as a carbon scrubber, we can decrease their emissions while also providing a cost or a benefit to this algae production. And even something such as moving cultivation offshore to these hypoxic zones, and possibly having areas out in the ocean where these, although the Navy carriers are going to be nuclear powered, the planes on them are not. And so imagine being able to fuel these planes out in the ocean and staying out for extended periods of time without having to come back for refueling. I'd like to thank a great amount of people, Dr. Chris Bachman, my parents, Roger Monger at the AFB lab, Marcella Molinax again, Dan Drumheller of Valley Precision Machining, John Wild, who helped out with 3D printing of my model, Dr. Tony Chen, who helped me with my heat transfer analysis, Mark Starnes of the JMU Machine Shop, and the entire algae team. Let's take any questions now.
Is there an algae that's better suited for this?
There are currently, again, there's wild type algae. There are a few that are high yielders, but again, it will be the genetic development of an algae that is specifically made to grow in fast rates, even have thinner cell walls for more easily lysing the cells to release this algae. Even, again, that oil content. So there are certain algae that are being developed right now just through that selective breeding, but it really will be genetic modification that I believe will industrialize this agriculture. Yes?
You said in the last slide that you thought algae fuels would be a co-product, a more cost-effective alternative. What other alternatives do you have in mind?
So there are, I'll use the antioxidant astaxanthin as an example. This is the antioxidant produced within these algae, eaten by krill, which are eaten by salmon even, that produce that red color in the salmon and produce that high antioxidant benefit. These algae still produce that in addition to these lipids. And so I believe that the technology will be driven by wanting to get that. The astaxanthin was the $5,000 a kilogram supplement that I was talking about. And so the technology will be driven by wanting to get this astaxanthin and using the fuel that you can sell as a co-product. I don't believe that will be the main point of growing the algae. Yes. Thank you. Yes.
Yes, I was wondering, what temperature does your condenser run at? Do you know what, like, the hexane vapor pressure is?
That was I was running just in ice water, so at about as cold as we could get, so as close to 0C as possible. I didn't get to measure that pressure, but I believe that since the entire unit is open, I believe that at some point it all comes back to atmospheric pressure. I didn't necessarily know the pressure.
No, I meant the vapor pressure of hexane at that temperature. It'd be like a handbook kind of value.
Oh yes, I know that the vapor pressure is enough so that at atmospheric it's volatile. So I'm assuming that at those higher pressures it really is much higher than that. Does that answer your question?
I mean, ideally at the condenser temperature, the vapor pressure would be very low.
I'm sorry. I was thinking what was coming into that condenser.
No, I mean,
yes. So it does. We are getting liquid out of this condenser, and I can actually provide a video here. It looks like it was taken vertically, but you can see what we're working within a fume hood. It's going a little bit slowly, but you'll be able to see that we are getting a liquid hexane back out of this, and I believe that the vapor losses that I was talking about before had to do with the way that we were feeding the system. Again, working all within the fume hood that we developed. This normally should only be about a minute, but are there any other questions that I can answer while we're doing this?
Did you have any hurdles that you had to overcome while you were going forward with this project?
Absolutely. As I mentioned, the fume hood development, when working with the JMU safety officials, as I said before, intentionally evaporating a highly combustible product is something that it's a little bit of a liability. And so by developing a fume hood that has a number of air changes per minute, we're able to keep hexane out of that lower explosive limit concentration and thereby make it just a much safer process to work with.
I don't think anybody saw it in here, but he actually designed and built the fume hood. It's an expensive unit. It'd be like $10,000 to install it. And so we had a limited budget. And so I put Remy on the case, essentially design and build within a certain dollar amount. And how much did I give you?
Under $500, and this was sourcing explosion-proof fans and motors from, I believe the motor came from an old paint mixing device, and the explosion-proof fan really just had spark-proof aluminum, which is what it was made out of. These were damaged goods. That actual fan that we got just had a couple of dings in it, and we were able to get it at reduced cost and develop this. Okay, it looks like this really isn't going to work. I apologize.
Could you tell them what was in that video? The last video?
This was us running the actual algae oil, and that was what I passed around. That is only about a 1/6 or a 1/7 of what we actually got out, but we did develop enough, or we did get enough of this algae oil to run it through this system, recover that hexane, to actually get something that we could work with.
Sorry to stop you, but we need to start on the next presenter.
I'll answer yours later.